So what we're going to do in this video is we're going to look at the process of model selection. In another video, we looked at sort of the basics of how to construct multiple regression models, and we identified that sometimes the p-values for individual coefficients are potentially problematic. How do we build good models that have coefficients where all of them pass muster in terms of our significance level? Do we include them? Don't we include them? So if we have too many variables in the model, we run the risk of overfitting the model, which makes them worse predictors because they're trying to model too much of the noisiness in our data. So instead, what we want to do is we want to include only variables in the model that are actually doing the job of doing the predicting, again, by extracting those variables that have p-values which are too high, that in those individual coefficients are indistinguishable from zero. We want to keep them out of the model. Now, there's a couple of different procedures that we can go ahead and use in order to select models for, select variables for a model. We're going to look at specifically backward selection. This is a procedure where we build the model basically with all of the variables we have available, and then we systematically, one variable at a time, remove those variables whose p-values are too large to be predictive, that they're not contributing to the overall value of the model. And then eventually what we get to is a place where all of the remaining coefficients have significance, have p-values below the significance level we've chosen. If we want fewer variables in the model, we can set our significance level to be lower. If we want sort of more variables in the model, we can set our significance level to be a little bit higher. But the idea is that whatever that threshold is, it gets typically 0.05, but whatever that threshold is, we want all of our variables to individually have significance in our model. Now, we're going to use the backward selection because I think it's the sort of easiest to follow and process, because we're essentially working backwards from all of the possibilities and then taking things away until we get everything working. But there are other methods for doing this. There's a forward selection process where you basically start with a variable that has the highest correlation, and then you start adding variables into your model one at a time. And then if they pass significance, you leave them in. And if they fail significance, you pull them out. Sometimes you will get sort of weird behavior sometimes happening. You'll put in another variable and it will make the variable that you started with less significant. But this general process of adding things to the model, and then just not keeping it if it doesn't contribute to the robustness of the model. There's stepwise selection where you can either add or subtract variables. This is sort of a less linear approach. But again, it is generally a sort of procedural step where you start someplace and then you add or subtract variables. Maybe you have some prior information that suggests, like, I know I want to include these 5 variables, and then you pick and choose from ones that are remaining. But that is sort of a combination of the forward and backward selection. And then there's best subset selection. Now, this one is computationally quite intensive because basically you're trying to check like all the possible combinations of models, all the 1 variable models, all the 2 variable models, all the 3 variable models, all the 4 variable models, and so on, until you find sort of the best model for the number of variables that you're looking for. It's because you're testing all the possible combinations, the more variables you have, the more there is to test. And so typically we don't really do this in Excel, unless you're only dealing with maybe 2 variables. All of these procedures can tend to lead you to different models. So there's not like one perfect model for all of these different combinations of variables. Sometimes they end up producing the same collection of variables, and sometimes they don't. And it's important to sort of know what the selection process was and how it was executed if you want to reconstruct the model that another researcher or your instructor or your student, in my case, might have used. So I tend to use the backward selection process because at every stage there is a particular choice, a clear choice that you should make. And if you follow that procedure, then everybody should end up with the same model if you're using that selection process. Sometimes these forward selection or stepwise selection, because you have different choices that you can make at each stage, you can use the same process and then still end up with slightly different answers. Now, this process can take time. If you have a lot of variables, then you, particularly if a lot of them are not particularly significant, you can't like skip over, like remove a bunch of variables all at the same time in order to save time, because as you remove variables, the p-values of the other variables will change. And particularly, we saw in the last example, there were two variables that had a strong collinearity, a strong correlation, and variables that should have been independent. If you remove one of those, then the p-value of the other one could be affected much more significantly. And if you happen to remove both of them, then you're losing all of the information that either variable included. So the procedure here, it's important that you only go through one variable reduction step at a time. Don't remove 2 or 3 or 4 variables sort of all at one fell swoop. It may seem like it's a waste of time and you're going to end up removing them all, but because there are potential complications, this isn't always going to work. And you do need to be careful about it because those p-values will update as you start removing things. So let's go to Excel. I have a data set on election results from lots and lots of elections in the United States, and see if we can sort of predict the percent vote from all of the variables that are available to us, and go through this selection process until we get the best model. It may not be a very good model, but the best model we can get. All right, so let's go over to Excel. All right, so we have, again, election data starting in 1880 all the way to 2000. So this is post-Civil War. We have data on the vote, that's what I'm going to try to predict. We have information on the party that won. We have information on the duration of the election. We have whether or not there was a war going on at the time. We have economic growth, we have inflation rates. And so we have a bunch of these variables, and we want to predict sort of the vote percentage. Now, in order to predict the vote percentage from all of the other remaining variables, the other remaining variables do have to be contiguous. I've noted this in a previous variable. If I want to include year as a potential variable, which again could be contributing, there might be a trend in time, then I can't actually put vote here. I have to move it around. So I'm going to reconstruct my variables with all of my X variables next to each other, and then I'll put vote. It can go on either side, but I'm going to put it out on the right side. Now, again, one thing that we can do here is we can try to make scatter plots to make sure that there's no nonlinearities and things like that. At a minimum, it's a good idea to make a correlation plot to, again, identify things like potential collinearity problems or things like that. Labels in the first row, output range, we're going to put you there. And again, the ones on the diagonal are correlation with itself. So of course we would expect them to be highly correlated with itself. And then we just want to look through here, particularly in terms of the vote. All of these seem to be very relatively small correlations. The highest one is with economic growth. That's certainly something that we hear a lot about in the news. If you follow politics at all during a presidential year, if the economy is doing well, the incumbent tends to do better. And if the economy is doing poorly, then that tends to be bad. Inflation has a negative effect. But let's look at some of these other ones. Nothing among the other variables seems particularly high, except for this one. War and quarters. But it's not 0.9, so I'm not too worried about it. If we find that we end up removing one of them, we may see a bigger effect on removing one of these variables versus the other one. But that is not like a major significant problem. It's, again, as I said, it's not a 0.9. 0.9 and 0.8s and things like those are the kinds of things that we worry about when we talk about collinearity. All right, so we've done our our correlation analyses. Again, we could, there's a lot of variables here, so I'm not going to do it, but we could create individual scatter plots if we're worried about a potential nonlinear effect. The scatter plots might reveal that. One scatter plot per match up with the vote percentage. But I'm going to assume linearity, and I'm going to just go ahead and create our data analysis toolpath, regression analysis, and work on our backward selection procedure. Now, we want to put the Y range to be our vote. And the X range to be year up to quarters. Output range. I'm gonna put that out here. And we get a bunch of residual plots. We get one for every variable. Year doesn't look too bad. Party, this is basically Republican or Democrat. That's a good reason to start post-election because there have only basically been two parties since then. Again, this is only a 0 or 1. Duration. Nothing particularly troublesome there. War. Growth. I'm going to try to pull these down so I can see them all. Growth. Orders. Inflation. None of these residual plots look particularly troublesome, which is definitely good news. I don't think it's orders. Okay, so residual plots don't look like they're particularly problematic. So let's look at the rest of our output. Now, again, what we're looking for in backward selection is we're looking at essentially the p-values for our individual coefficients, because these are going to determine whether we keep or remove the variable. So our significance level for the whole model. There is something going on in our model that is being predictive. Our R squared value isn't that great, but 64% is better than half, so that's good. Now let's look at our variables, and what we see is that the highest p-value is for year. And I'm going to highlight that. That's the highest p-value. So what we should do is we should perform the analysis and remove year from the analysis, from any future analysis. That is the highest p-value. That's where we begin. Now, the one exception to this would be if the p-value actually, the highest p-value was the intercept. You might remove the intercept and then find out that that makes all the other p-values good, or you may want to eliminate variables that have very high p-values before you tackle the intercept. But if you just go through the procedure of pick the highest p-value, remove it from the data set, then that's a nice procedural method to follow. So we're going to redo this without the year variable. Now, fortunately for us, the year variable was the first column. And so resetting up our data analysis toolpack results will be fine. I'm going to leave out the residual plots for the future ones because as they sometimes turn up in strange places. And then we'll just rerun this and see what happens. All right, so let's go into data analysis, rerun our regression. Now, the one thing I'm going to change is I'm just going to make my K, turn it into an L so that it doesn't start with year, it starts with party. And then I'm going to change my output range location to this. And then also I said I was going to turn off the residuals and plots because they can tend to get in the way. When we get to the end, we can then do residual analysis of what is left. All right, so step 2 of our analysis, we've eliminated the year variable. And now let's look at our significance level has actually gone down, I think. Yeah, that's good. All right, so then let's look at where is our next highest one. It looks to be this one. So whether there's a war or not does not seem to affect the percentage of the vote that people receive. That's interesting. But let's go ahead and remove it. Now, here's the problem. War is in the middle of our variables. So what we're going to have to do is, again, we're going to have to recopy all of this, but then remove war from the middle. I don't need year. So I'm going to copy everything, and then I'm going to remove war. And again, don't, every time you do this, you do want to be careful about not deleting your original data, make copies of things, and then remove from the copies. All right, now let's redo our analysis. The Y variable, I've now copied it, so it's in a different location now. My X's are not over there. They're now over here. And I'm going to put my output. Again, don't overwrite old output. And then go. Now notice that even though I had two p-values that were both above 0.5, which is very high, I did not remove them both at the same time. I only removed one of the variables. And now, again, my significance level has gone down again. That's excellent. That means there's more good stuff going on in the model. Let's look at our p-values. This is still, person is still very high. So again, we're going to remove that variable. Now, the fact that that was the high one from before and it's still high was not terribly surprising because it was very, very high. But all of the other p-values have changed. And so you never really know, especially when they're borderline, whether or not it's safe to just remove a whole bunch or not, because there are effects that can happen. So now we removed one, we're going to come back. We have another one that we can remove. Let's remove that one. And again, I'm going to make these copies and then now it is also honestly, if you're only doing one analysis at a time, putting these in separate sheets is probably a little bit easier to manage all of the data. But I have other sheets going on here, so I'm trying not to do that. All right, where is my Y value? It's here. The Y value is just one column and it hasn't really changed. And so if you don't want to keep updating the Y value and just work on updating the X values, that is perfectly okay. And then we need to change where the output is going to go. From there to there. All right, so again, this has gone down again. Let's look at all of our p-values. That's very low. This one is a little borderline. That one looks good. That one looks good. That one looks good. That one looks good. Okay, so this one then, the party variable, this one is kind of borderline. If your significance level is actually at 0.1, you should keep this. But this is suggesting, in fact, that it's not really statistically significant at the standard cutoff level. And so we're going to do one more. We're going to take party out. And I'm going to highlight it just to remind us this is what we're doing. We're removing anything that is above the significance level. And so when I redo, party is already on the end. So I can just put a new output here. Everything else will be contiguous, so I don't have to worry about recopying things. I can just take out BS and turn it into BT. And now I think I'm going to be done. So this was the highest one. It was barely above the threshold. So I'm going to redo my residual plots for the remaining variables in order to do my final analysis. And now I'm going to hit OK. And who knows where those residual plots ended up. Again, the nice thing about putting them on different sheets every time is that you don't have to worry about stalking your residual graphs. Okay, now this is interesting. When I removed the party value, my inflation suddenly went from being 0.03 which is nice and low, to 11. And so I think what this suggests to me personally is that for my money, I actually think I would want to actually keep party in the problem. Look at my significance level. It actually went up instead of going down. The p-value for my full model, my r squared value went down to 57 instead of being at 63. And so that's a sign that maybe we've gone too far. And so I think this is going to be the preferred final model. It explains more of the data. This is kind of borderline. And we know that inflation has an effect on elections. I mean, that's sort of one of the tropes of listening to political season. If inflation is too high, that's bad. And the fact that that sort of went away when we eliminated party suggests to me that what we should not do is continue to eliminate variables, that there are effects on these variables, but typically what you want is you want the p-values, as we've seen in previous stages, to go down. And this did not actually go down. Another thing that we can look at is the standard error. And again, the standard error in this smaller model went up compared to the slightly larger model with this party variable included. And that's also a sign that our predictions are doing less well. And it's a small difference, but the fact that the r squared value and the residual error value went up also, and that weird p-value effect, that's a sign that I think it's time to stop deleting. So backward selection, again, start with a full model, go backward one variable at a time until you get to a model, ideally where all of the p-values are below 0.05. And again, there are possibilities about when there are different criteria for when you can stop, but continuing to delete does not seem like that's going to improve our model. So go backwards until you get to a model that seems to work the best.